Okay, well, I'm going to try something new for this class because we have a test on Tuesday and we had our last lecture that was covered on the test, that will be covered on the test on Thursday. I don't have a chance to review some questions that you guys had from your decks. So I'm actually going to create a video that you guys can watch and hopefully I can clear up some of the questions because I did get a lot of questions about this topic because it was confusing. So I want to remind you, we're going to start with free energy and the second law of thermodynamics. Remember, the second law of thermodynamics states that a chemical reaction can only proceed spontaneously if it results in a net increase in disorder, okay? And we measure order by free energy, which is denoted as G, and this is the available energy or capacity to do work. Okay, so anything that has high order has a high free energy, has a high G, and anything that has a disorder has a low free energy and a low G. So the example I gave you guys was a dirty room versus or a clean room versus a dirty room. When you clean the room, it has high energy, high free energy, and as you make it more and more dirty, it goes into a state of disorder where it has lower free energy. Okay, so let's look at a chemical reaction, all right, over here on a notepad. Let's say we have the reaction, okay, A turns into B, and this is a reversible reaction, meaning that B can turn back into A. And so what we want to know is in which direction is this reaction most favorable? So keeping the second law of thermodynamics in mind, we know that the direction a reaction is most favorable is when it goes from high order to low order, or high free energy, G, to low free energy, G. Okay, so every molecule has its own free energy value. So for example, A has a G and B has a G. And to calculate the changes in free energy of a reaction, you can basically draw this reaction two ways. You can draw the reaction A turns to B, or you can draw the reaction B turns to A. Okay? To calculate free energy changes, all you do is you take delta G, which is the free energy change of reaction, and you take the free energy of the product, in this case be B, minus the free energy of the reactant, in this case be A. Likewise, in this equation, you would take delta G, would be the free energy, okay, of the product A, minus the free energy of the reactant B. So to look at whether or not which one of these directions is most favorable, you have to know what the free energies are. So let's just do an example, and let's give some values here. So let's say the free energy, so G to A, is, let's just give it 4. Okay? And let's say the free energy of B is 2. Okay, and free energies are always written in kilocal per mole. All right? So if you go back to our equation, the change in free energy of A being converted to B is going to equal 2 minus 4, which equals negative 2. The change in free energy of B going to A is going to equal 4 minus 2, which equals 2. Okay, so in any reaction in which the change in free energy is negative, so in this case A going to B, change in free energy equals a negative value, this is called exergonic. You have to forgive my handwriting, it's quite bad. Exergonics means it's releasing energy. It's going from a state of higher free energy to low free energy, which means, according to the second law of thermodynamics, that this is a favorable reaction. Okay, favorable. Over here, you can see that the change in free energy is a positive value. Okay, it's plus 2. And that means that this reaction is endergonic. Endergonic. And that means that it's unfavorable and it would require energy to occur. Okay, so we have two equations here, and what this tells us about our initial equation, let's rewrite our initial equation, is that the direction from A to B is much more favorable than the direction from B to A. And you can draw it with a large arrow in the favorable direction and a small arrow in the unfavorable direction. And that'll tell you that this is favorable. Okay, I apologize for my handwriting again. It's terrible. So we know that our reaction from our delta G calculations is more favorable to go in the direction of A to B than the reverse. Okay? But if you let this reaction go as far as it can go, it'll reach a point where the rate, okay, of A being converted to B equals the rate of B being converted to A. And this point is equilibrium of the reaction. So this is what we call equilibrium. And so even though this reaction is favorable from A being turned into B, if the concentration of B gets to a point where the rate being converted back to A is the same as the rate being converted to B, okay, you'll reach equilibrium. So therefore, the delta G values actually can change based on whether or not, based on the concentrations of the reactant and the product. If I have a system where I have almost all A molecules, you're going to have a favorable conversion to B. But if all of a sudden I add to that system 1,000 times more B molecules, I've immediately changed those reaction kinetics, and I've changed my reaction. So to get around this and talk about free energy changes on a general level, we have a new value called delta G naught, which is the standard free energy change. Okay, this is standard. Standard, I'll just do FE, free energy change. And what this means is whether or not a reaction is favorable when all the molecules in that reaction are at 1 molar concentration, a pH of 7.0, sorry, it looks like a 9, but 7.0, okay, and 37 degrees Celsius. So now we can talk about reactions on a general level about whether or not the reaction is just favorable at these most ideal conditions. Another thing to keep in mind about equilibrium is that if you look at free energy in a reaction in terms of equilibrium, you'll find that at equilibrium, free energy is at its lowest point. Okay? So as the reaction goes to equilibrium, the free energy is going to drop to its lowest point. So we can calculate the point at which a reaction reaches equilibrium by looking at the equilibrium constant. So this is denoted as KEQ, and all you do is you take a reaction and you bring it to equilibrium, and you measure the concentration of the product, in this case B, divided by the concentration of the reactant, in this case A, and that's your equilibrium constant. Okay? Whatever value that is, that's if you're at that value, at that ratio of product to reactant, you'll be at equilibrium. So if you look at a graph down here of the product to reactant ratio, let's say we're here. So this is our equilibrium constant, okay? And you measure free energy on the left. What you'll find is that the free energy is at its lowest point at equilibrium, and as you go away from equilibrium in either direction, the free energy will increase in the system. Okay, so free energy not only tells you which direction a reaction is most favorable in, but it also tells you how far away from the reaction, how far away from equilibrium that reaction is. So there's an intimate relationship between the equilibrium constant and free energy. And so if you know the free energy change of a reaction, okay, you can calculate at what point will that reaction reach equilibrium constant, okay? So KEQ equals 10 raised to the minus delta G naught divided by 1.42. Okay, so let's say, for example, that our reaction A to B that we know is favorable has a delta G naught of minus 2, which is what we were using as an example earlier before. Okay, what that means, and I'll spare you the math, but that the KEQ equals 25.1, which, if you remember, that means that the ratio of the product over the reactant equals 25.1. So at equilibrium, because this is such a favorable reaction, there's going to be 25 times more product than there will be reactant. Likewise, if you knew the KEQ of a reaction, okay, you can calculate the delta G of that reaction, and that's just simply a rearrangement of this equation, 1.42 log base 10 KEQ. I'm sorry, this is, erase this. There we go, this is delta G naught, sorry about that. Okay, so if you think about this, you can tell from a reaction whether or not that reaction is favorable. You can tell from at the equilibrium point whether it's a favorable reaction. And if you do a lot of examples and you kind of look at this equation over and over again, you'll realize that if the KEQ is greater than 1, okay, the delta G for that reaction is going to be negative. Right? If the KEQ is less than 1, the delta G of that reaction is going to be positive, meaning that this is going to be favorable, this is going to be unfavorable. And if the KEQ is equal to 1, right, there is no free energy change in the system. Delta G equals 0. What that means is that if at equilibrium there are equal number of products and reactants, okay, that reaction has no favorability to go either direction. There's 0 free energy. Okay, so that's the relationship between delta G, chemical equilibrium, right? Favorable, unfavorable, and different reactions. So we've been using this hypothetical A turns into B. Let's use an actual real example. Okay, so let me go over here, get a blank piece of page. All right, so let's use the example. Sucrose plus water, this is the example I gave in class, gets turned into fructose and glucose. All right. So what I want you to tell me is whether or not this reaction is favorable, whether the favorable reaction of sucrose into water being turned into fructose and glucose. So we can calculate the KEQ by writing this equation. KEQ equals the products, so fructose times glucose. Because there's two products here, we multiply them, divided by sucrose. And let's just say, for example, I gave you a hypothetical number that the KEQ here is 140. So what that means is that at equilibrium, there's 140 times more product than there is reactant. Okay, this tells you that this reaction is probably going to be favorable in that direction. And to prove it, you can just do the equation, delta G naught equals minus 1.42 log base 10 of 140. Okay, and that actually comes out to equal negative 3.05 kilocal per mole. So just by knowing the equilibrium constant of reaction, you can tell whether or not that reaction is favorable or unfavorable. And likewise, you can tell that if there's a favorable reaction, typically that reaction is not going to reach equilibrium until there's a lot more products than there are reactants in that reaction. So if on the exam, say, I think there's a question like this on the practical exam, if I give you a question that gives you a reaction A to B, and I say at equilibrium, okay, A equals 4 millimolar and B equals 2 millimolar, right? And I ask you, let me fix this, and I ask you whether or not this reaction is favorable or unfavorable based on what you know here. Well, all you have to do for this question then is figure out the KEQ. The KEQ is the ratio of the product here, 2 millimolar, divided by the reactant, 4 millimolar, okay? And that equals 0.5. Well, we know from our math equations that obviously you don't have to memorize, but you should just be familiar with what they say. We know that a KEQ of less than 1, okay, equals a positive delta G naught. Whoops, forget the C. So this tells you from this KEQ alone that this reaction is unfavorable to occur in this direction. It'd be more favorable to occur in the reverse direction, B to A, because at equilibrium, there's actually a lot more reactant than there is product. Okay, so if I give you any numbers for two reagents in a reaction, you can figure out what the KEQ is, and then you can actually predict whether or not it's a favorable or unfavorable reaction. Okay, so I hope this makes sense to you about delta G's, KEQs, and the relationship between the two and what delta G's are really saying to us about a reaction. Again, forgive me for my handwriting, it's kind of hard with this pad, but if you have any questions at all, if you're still confused, just come see me, shoot me an email, and I'll be more than happy to help you with any questions you have. So I hope this helps. If you want to learn about, or you're confused about some of the other things we talked about in that class about coupling reactions, you can watch the next video where I cover coupling reactions to each other, okay, coupling unfavorable to favorable reactions.